Yeah. All right, 121 students. Let's see. Let's look at some more chapter 32 examples. And I told you I would do 8 of them. Hopefully that's not too many here. 57, 42, 54, and 59 were the second set of 4. So let's give that a shot here. I printed those also here. So here is the 57. Oh, it looks like it's a magenta one. It says a toroid is shown in the figure. So here is this kind of this donut shape or bagel shape. Let's see, do I have anything looks like that? I don't have anything kind of close by here that looks like that shape, but it wraps around in a circle, so they've kind of trying to make a three-dimensional view here. It says it consists of n turns and has a rectangular cross-section. So here is the rectangular cross-section. Its inner and outer radius are A and B, respectively. Show that the inductance of this toroid is given by this equation. All right, so this sounds a little bit like the one I did in the first example where I had to work out the induction of a solenoid. Also did it in class. So let's work through that problem. Let's see. B here says, use this result, compute the induction of what if in problem 8 an approximation, well, let's worry about that when we get there. So let's do A, and I will start with the general idea of Faraday's law. Faraday's law says you'll get an EMF, and if it's on itself, we call it a self EMF, and of course it opposes the change, so we call this a back EMF from our inductor here. But let's see if we can rearrange this until it looks like a negative, a bunch of stuff, and then how the current changes with time. And all of this stuff would be the inductance of it. And so it looks like it depends on the number of turns. Remember when we did the solenoid, it depended on the number of turns twice, because the first n is because of the Faraday effect, and the second one is because the flux actually comes from the object itself. So not a surprise that it's n squared, and then some of geometry features, the a and b radius, the height. All right, so let's give this a try. All right, so I'll do this first step where the flux is the b dot dA. And the first step, of course, is to take the dot product, B, D, A, and cosine of theta. Now, for something that looks like this cross-section, let's see, as the field, maybe I'll try to finish the circles here. But the field is in the toroid part. It's in the tunnel part. And it is wrapped around the tunnel. So if I take a cross-sectional area, the direction of the area vector would be right down the center of the tunnel. And so is the magnetic field. And so that tells me the angle there is 0. Okay. The other thing is that the magnetic field from a toroid has this kind of an equation. N is the number of turns in the toroid, I is the current in the toroid, and R is the distance as measured from the center of the donut hole part. So right here, the axis of symmetry, the distance where A and B is measured. So that's good, and then we would have this dA. Now, if I pull out the things that are constant, that n would come out with the first n, making an n squared. I'd have a mu naught. I'd have a 2 pi. And it looks like the current is pulling out in front of the integral, but not in front of the derivative of time. Okay. So that's good because that's this part of the equation, and everything else then is going to be this inductance piece. All right, so keeping that in mind, I've got this integral to do of 1 over r and then times this area. Now, let's see, the area, maybe I'll just make kind of a little rectangle here to represent this cross-sectional area. So this is a distance A, and then this out here is a distance B. So as I'm going to add up in this rectangle, because the field changes with R, I'm going to go ahead and cut my cross-sectional area into little rectangles that are going to have a height of H and a thickness of what we might call a dr. And so a little bit of area would be H times dr. And then we would add up from this first rectangle, which is a distance of A, until we get to the last rectangle. And so this H can be moved all the way in front of my two calculus operations. And then I have just simply this integration of dr over r, which is ln, with the limits from A to B, which I can move that in front of the time derivative. And so there I have what I was hunting for. All of this stuff in front of the time derivative must be the inductance. Well, not counting the negative sign. So this would tell me the inductance is an n squared mu squared h 2 pi natural log of b over a. And I think that matches what they wanted me to show. Yeah, mu naught n squared h. Okay, good. 2 pi ln. Yeah, perfect. All right, so there's the first part. What's the inductance of a toroid? That's something we hadn't really done. We've been doing a lot of solenoids, but not toroids. Now, part B says, using this result, compute the inductance of a... Okay, let me put in some numbers here. Starting with the mu naught, 4 pi times 10 to the minus 7. Here it says a toroid that has 500 turns, so there's the n squared. Let's see, gives us an A and a B, and oh, here's the height, 1 centimeter. Now, I'm going to go ahead and do that in meters and kind of be a little careful here with my units. Over 2 pi. And then ln. And of course, now here we have a ratio, so it doesn't really matter what units we use. So maybe I'll just go to meters just to be safe, but B over A then would be 0.12 over 0.1. And meters would cancel with meters or whatever, centimeters with centimeters. And we have a ratio, the units don't matter there. All right, now maybe down here I'll just kind of mess with these units. And one of the ways I was saying is you can think of mu naught in a lot of ways. I always just find this the easiest one, the solenoid, because the mu naught then is directly tied. And so I remember the units on mu naught by saying it's the Tesla times a meter divided by an amp. And so that's the units of mu naught. And then in this case, if I multiply it by this unit, which is in meters, and there's no units here, no units here, and no units here, I get this Tesla and meters squared. Actually, maybe I should then switch the the Tesla into what it means. It means a force of 1 Newton when you have 1 coulomb of charge moving at 1 meter per second. So there's my Tesla. And I get the meters squared over the amp. Because one of the meters cancels off. And then if you put the Newton with the meter, that's a joule. A joule per coulomb is the volt. And then you would have amp per second. And that was our definition of inductance. It's how much voltage do you get when the current is changing at 1 amp per second. And that is a Henry. So there's my Henries. So these are pretty complicated units, probably the most we'll see this semester here. And so that works out well. And so doing a calculation here, I've got a 4 pi times 1 times 10 to the negative 7 times a 500 squared times a 0.01. I'll go divide by 2 and also another divide by pi. Then a times a natural log. And if it'll be okay, I'm just going to do a 12 over a 10 and forget the decimal place and hit enter. And so we're looking at 9.11 times 10 to the minus 5 Henries. Maybe best to write it as 91.1, and then these would be micro Henries. Yay! Okay. Now let's look at C. And I started to look at C, and it kind of didn't make sense. It says, what if, in problem 8, an approximation equation for the induction of a toroid when R was much greater than little r was derived. To get a feel for the accuracy of this result, use the expression in 8 to compute the approximate induction of a toroid that is described in B. How does this result compared to what you got in? Well, let's see. Just to do that, let me come back here and grab my textbook. And let me open up here to chapter 32 and see what they're saying here in number 8 here. It says a toroid with a major radius of r and a minor radius of little r. Oh, okay. So maybe you got to go to the next page, and now it's making sense. The big R is the radius to kind of the center of the tunnel here. And the little r then is the radius of the tunnel itself. It's kind of shown right there. So in other words, for part C, the capital R, something like this, would be to the center of the tunnel. So that would be the average of A plus B. Okay. And then the little r would be kind of the size of this tunnel, and so it would be B minus A. So for the numbers that they just gave in this problem, let me get my book out of the way here. Okay, so for this particular problem, let's see. If problem A, approximation equation derived the inductance of a toroid, R much greater than R was derived. To get a feel for the accuracy of this result, use the expression in 8 to compute the approximate induction of the toroid of B, and then how does this result compare to B? Okay, so let me get the capital R, because I'd add the two together and divide by 2, so I'd get their average. So halfway between is 11. So we're talking about 11 centimeters for a capital R, whereas actually, my bad, the difference between them would actually be 2R, wouldn't it? It would be the diameter here, as they showed. Okay, so divide that by 2 to get the radius. Okay, so they have a difference of 2. And then if I divide that by 2, that's 1 centimeter. So we are talking about a situation where R is quite a bit bigger than little r. It's 11 times bigger to be exact. And so that's a pretty good separation here. Okay, so using this information, let me jump back to problem 8. And it looks like they did an approximation and said L equals, let's see, what do they got here? They say it's approximately equal to, let me switch my paper on top of my book so you guys could see it. Let's see about that. So L is approximately mu n squared over the area, or times the area, divided by 2 pi capital R. Okay. And that's actually, I see what they did. They just made a uniform field, because this would be like a solenoid, where this 2 pi R is the length of the solenoid, and we had, for a solenoid, mu n squared A over L. So, looks like in number 8, they just say, take the field to be a constant in there, since the radius of the tunnel part doesn't change much, and you can treat it then just like a solenoid. All right, so I see why they're saying this is not equal. I should put approximately equal. All right, but let's do these numbers. So this would be 4 pi times 10 to the minus 7, and we would have our 500 turns squared here for this problem. I believe that's what the number we're in. Yeah, 500 turns. The area would be pi times little r squared, and the circumference would be 2r times or 2 pi times the big R. All right, so putting in my numbers here, 4 pi times 10 to the negative 7 times 500 squared times pi times little r. And I guess we said little r would be 1 centimeter, 0.01 squared. Then divide by a 2, divide that also by a pi, and then divide that by this capital R, which we said then would be 11 centimeters. All right, and I get 1.43 times 10 to the minus 4 henries, or 143 micro henries. And I guess that's approximately the same. That's, I don't know. Not real crazy about that answer. Makes me want to look to make sure I did all these numbers correctly. Well, they look okay. All right. So, yeah, it's reasonably close, but why make that approximation? It wasn't real hard to calculate that one, although it was a magenta one. All right, well, let me not dwell too much on C, but hopefully you got the main gist of this, which was A, and so now we know how to get the inductions of something that's in a toroid shape. All right, so let me go on to the next problem, number 42 here. Okay, so 42 says the switch in figure 42, this picture here, is connected at point A for a long time interval. So we just have an RC circuit here, a DC RC circuit. So we're gonna build up a charge on this capacitor if we leave it closed at point A for a long period of time. After the switch is thrown to B, okay, so hopefully we can see now what's going to happen is you're going to make a connection over to here, and we're going to have our LC circuit. So this is where we're going to get those oscillations we talked about before. And, of course, the energy is going to come from an initially charged capacitor. We did a problem in the last video where the energy came from initially an inductor that was flowing current. And in class, we derived it when the capacitor was initially charged and started with the energy. So that's what we're going to have here. Okay. So after the switch is thrown to B, what is A, the frequency of the oscillations of the LC circuit? Okay, well, that's probably the easiest one because the omega was 1 over the square root of LC. If you remember, we worked out that second-order differential equation by inspection. Now, I think they asked for the frequency, not the angular frequency. So let me replace omega with 2 pi f. And so the frequency would be 1 over 2 pi times the square root of LC. Okay, so grabbing my calculator here, maybe I'll start with the L and the C. So here's the C, 1 microfarad, and the L looks like 1/10 of a Henry. So I'll hit enter, that's LC. And let me then take the square root of that. And then let me combine that with a pi and combine that with a 2. So there's the denominator. So if I take the inverse of that, I guess we're looking at about 503 hertz as this would oscillate back and forth. Okay, actually 503, that number, that 500, these are pretty close to the numbers we're going to do in lab coming up. We're going to have an inductor and a capacitor, and they're going to have these values. Interesting. Okay, but anyways, that's its natural frequency. So what frequency of oscillation? B, the maximum charge that appears on the capacitor. Well, this, separating this part of the circuit off, this is just a charging up capacitor. And after a long period of time, there'd be no more current here, so no more voltage change on the resistor. So that means this capacitor builds up to block this 12 volts. So we're going to get 12 volts on this capacitor. And that would tell us the charge, because remember, capacitance is the charge over the voltage. Or in this case, since they're after the charge, let me rearrange this equation to say charge is capacitance times the voltage. So the capacitance is 1 microfarad, and the voltage is 12 volts. And if you multiply a 1 times a 12, you get a 12 micro. And remember, a farad is a coulomb per volt, so the volts would cancel off, and you're going to be left with coulombs. And so 12 microcoulombs then is the charge that appeared on this inductor. Okay. Now, moving on to part C of this problem, it says the maximum current in the inductor. Okay, well, this goes to an example I did a little earlier that says, let's do this in terms of the energy. Their oscillation is starting with this much energy, and it's all electrical energy. And so this is the maximum. And then later on, as it oscillates, the capacitor becomes completely discharged. But at that time, then the inductor has all of the energy. And so this maximum current, although it occurs at a different time than the maximum voltage, they must mathematically be the same. This fits that analogy of the pendulum swinging. And so when the pendulum swings up, it has no kinetic energy but a lot of potential energy. And a little bit later, it loses its potential energy and has all kinetic energy. And then later on, it goes back to all potential and no kinetic. And so that's what happens as the current oscillates here. It goes from electric to magnetic and back to electric to magnetic and just keeps swapping back and forth. And so that's kind of useful to then say 1/2 CV squared would equal to 1/2 LI squared. And the 1/2 would cancel off. And then taking what we already know, that the capacitance is 1 microfarad and the voltage is 12 volts, then we can take the inductance, which is 0.1, and then figure out what the current would be here. All right, so maybe I'll just take that as 144 divided by 1/10 makes 1,440, and that would be micro. And all those would come out to be amps, squared. And then I need to take the square root of that. So I guess I do need my calculator. I was looking like I wouldn't need my calculator, but I think I will here. Maybe I should just check my math. 12 squared is 144 divided by 10, and then micro. So let me go 1440 times 10 to the minus 6. And then let me take the square root of all of that. So there we go. The currents would be 0.0, I'll call it a 38 amps, or 38 milliamps would be the current. Yay! All right. So as it sloshes back and forth, what is the maximum current? And then D, what is the total energy the circuit possesses at 3 seconds? This one, we can go down a rabbit hole here and go nowhere of importance. We could look at the oscillations and say things like how much charge is on the capacitor after 3 seconds, and therefore how much energy is on the capacitor, and how much current is after 3 seconds, and therefore how much energy is on the inductor, and then add them together. But like the pendulum, as it swings back and forth, it's changing between kinetic and potential, but the total never changes. So you can just calculate the total energy at any point, down here at the bottom where it's all kinetic, or up at the top where it's all potential. And then likewise for this circuit, you can calculate the total energy at any moment in time, and it's the same for all moments in time. So the 3 seconds is kind of irrelevant here. And why don't we just say what the energy is to begin with, because we just did that right here. And so the beginning electrical energy is 1/2 CV squared. And so we've got a 1/2. The C is a microfarad, and the voltage is 12 volts squared. So this would be 144 cut in half, make us 72 microjoules of energy. And so that should be the total energy. Okay, good. And so there's another nice little example one. All right, how we doing on time? Oh, good. About on time. Let me try another 2 here. All right, how about number 54? Okay, so 54 looks like this. It says here, when the current in the portion of the current shown in this figure, okay, so looks like we have an inductor and a resistor in series between 2 points labeled A and B. When the current in the portion of the circuit shown is 2 amps, and increasing at a rate of a half an amp per second, the measured potential difference between A and B is 9 volts. Now, I suppose we should be a little careful on their voltage definition between A and B. But I think what they're saying here is A is higher than B by 9 volts, not the other way around. I think so. Let me keep that in the back of my head here and keep going along here. All right. But kind of depends on their definition of this subscript AB. The measured potential difference, that is, between A and B, and actually maybe if we are just consistent with our own definition, we'll be okay, is 9 volts. When the current is 2 amps and the current is decreasing at a rate of 0.5. The measured and it's increasing. Sorry, went too fast there. And it's increasing. So as we are trying to increase the current here, we would get a voltage change here, and it would oppose the change. So this side would be plus, and this side would be minus. In other words, as we walked the circuit, we would go down in voltage. We would have a minus L di dt. And then, of course, if this is the direction of the currents, we would also go down, plus, minus, on the resistor. So that would be a minus IR. And so they're both, I guess, a down of 9 when we go from here to here, or you can say it the other way around, they're an increase of 9. I think what I'm trying to say here is if I take the current on the resistor and combine it, the voltage on the resistor, and combine it with the voltage on the inductor, we're talking about 9 volts here. And they actually give me the current of 2 here. Let me just read it carefully here. Is 2 amps and increasing at a rate of 0.5. Okay, so this would be 2R, and then this would be L times 0.5, and that has to equal to be 9. So that would be my first equation of information, and of course there's 2 unknowns here, R and L. So then it says, when the current is 2 amps but is decreasing at a rate of 0.5. Okay, so in this case, as it is decreasing, the inductor would make this side positive and this side negative. In other words, this would be a negative number here. And of course, this would still be the same. You're still going with the current. So for this other case, I would say something like this, 2R for the voltage change here, and then this right here, this L, and then it would be a minus 0.5. And then that would have to equal decreasing at a rate of 0.5. Measured a potential difference of only 5 volts. So 2R minus 0.5 L equals 5. And so I guess I'll call that equation 1 and equation 2. And then fortunately, then, I've got two equations and two unknowns because they said go ahead and calculate the values of L and R. And so probably elimination method is the best. Just add these two equations together. 2R plus 2R make 4R. But a half a L plus a negative half of L is 0L. And that equals then to 14. And so solving for R, I can get 14 divided by 4, excuse me, which is 3.5 ohms. So there's the resistance. And then use that, and it doesn't matter which one, I'll grab the top one, but 3.5 times 2 makes that a 7, plus a half a L equals a 9. Subtract 7 from both sides is a 2, and then L equals a 4. So this should work then when, maybe I'll just double check, 3.5 times 2 is 7, and then half of 4 is 2, that makes a 9, and then over here we've got 7 minus 2, which is 5. Yep, perfect. And so there's our L and our R. But I think the big part of this was to, again, do kind of a Kirchhoff's loop here, or a conservation of energy, together with knowing that the voltage on an inductor is L di dt. Okay, so that one wasn't too bad. Conceptually, it might have been a little bit harder than mathematically. Maybe that's why they gave it a blue one. You got to be a little tough here conceptually. 59, a magenta one. Okay, well, and let's do the 8th example, or the 4th one on this video, and saying, all right, let's look at something, that's pretty complex here. We really didn't do anything quite like this problem. In fact, a couple thoughts come to mind. I think that the author wants you just to kind of write this out and as a general answer, and so I'll do it the way I think the author wants. Because if you kind of look at these resistors, they're not in series and they're not in parallel. So I think I'm just going to have to do some Kirchhoff's loop rule. Now, if you know a little bit more about circuits, we kind of touched on it. Let's see, an example I did in the last video. You might remember this one here. It was number 20 in the last video, where we said that it's not a surprise that a constant current source in parallel came out to be the same solution. What was the solution? Right here. The same solution as a constant voltage source in series because of our source transformation. And so this one kind of touched on some neat stuff that is really beyond where we're going in our class. Not that it's too hard to do source transformations, it's just that's kind of saved up for the circuits class. And this one right here is just screaming at me, hey, do this as a source transformation. So maybe I will when we're done, but for most of you, you don't know what that word source transformation is. But any of you who are in the circuits class and still listening when I'm done with all this math, maybe I'll come back and do this with a source transformation, and it'll make short work out of this one. But let's do it the way that I think the physics part of this wants to be, and that is, hey, look at a circuit, write out your equations, write out your conservation of energy, write out your conservation of charge, and you'll have a system of equations, and then solve the system of equations. And it sounds real simple, just conservation of energy, conservation of charge, and now solve the math. But it's going to be some pretty tough math questions, I think, here. And you can kind of see that they've even put an equivalent resistance, and that looks like parallel. Which, again, looking ahead, if you do a source transformation, that resistor becomes in parallel with that one, so not a surprise. And so this should be an interesting set of mathematics, and now I see why they made it magenta. This looks maybe a little brutal here. All right, so let's do this. Let's call the currents coming out of this source right here current number 1. It hits this node, it goes through this resistor, so I'll call it current number 2, or it splits off and goes through the inductor, which I will call it current number 3. So the node rule would say current 1 has to equal current 2 plus current 3 all the time. And because this is an inductor, which means the voltage changes with time, all these other currents are also going to be changing with time. That's what's going to make this a hard equation. We're going to have some derivatives here that are functions of time. But there's the node rule. Now let's do a loop. Let me do the left loop. I'll start over here and say, okay, here's the EMF. This would be minus I1 R1. When the switch is closed, then this would come down, and this would then be a minus I2 R2, and that would complete the loop. And so there's the conservation of energy on the left loop. And then let me do the conservation of energy here on the right loop. I'll start down here and I'll go against the current, so it'll be a plus I2 R2. And then I'll go with the current, so it's minus L di3 dt. And then that gets me back where I'm started. So here's the two loops and here's the node. This is our set of 3 equations. 3 equations, 3 unknowns. Sadly, the equations have a derivative in them. Or maybe not so sadly. That's what's going to make the math here kind of fun and kind of long to do. But I wanted to start here because this is the physics of it. Conservation of charge, conservation of energy. Now I have a system of equations. Now solve it. And I'll keep focused which current I want because it says here at time equals to 0, the open switch is thrown to closed. Use they even say, use Kirchhoff's loop for the instant that the currents and the voltage in the 2-loop circuit and show that the current in the inductor, so there it is given by this equation. So we're trying to solve for what I've labeled current number 3. And so maybe the first thing to do is to use the first equation and put it into here to get rid of all number 1s. Okay, so I'm going to take first equation and put it into second equation. So here's what will happen to second equation. It'll be E minus, maybe I'll try to put them both here. So E minus, and in place of number 1, I've got current 2 plus current 3 times R1. And then minus current 2 R2 equals 0. Okay. So I will call that my new equation number 2. And notice it doesn't have anything with current number 1 in them. And maybe I'll just repeat underneath it equation number 3. And so when I look at these 2 equations, I have 2 equations with 2 unknowns, current 2 and current 3. So that's my first step, is eliminating current number 1. Which, as a side note, you guys in circuits, that's kind of where you would have done if you kind of gave this a mesh current. So that would have gotten you right here to begin with. That's kind of the shortcut of the thinking of a mesh current. Okay. Well, I guess you would simplify this equation. In fact, let me simplify it here. So here's my EMF. And I have here a minus, let's see, why don't I put current number, no, I just realized if I did a mesh, well, depending on what I called it. Never mind. Let me just stay focused here. So this would be a minus current number 2 on both of these. and there'd be an R1 and an R2, right? Let's see, they're both minus, so there's the minus number 2, and then it would just be an R1 plus an R2. And then this would be minus an I3R1. Okay. So that's what I get here. Now, maybe the thing to do is to take this equation and solve it for number 2 and put it into this third equation, which has a number 2. So let me do that. So I'm going to go E minus I3R1 equals, I'm going to move this term to the other side, so it's going to be an I2R2 plus, or R1 plus R2, or current number 2 equals to E minus I3R1 over R1 plus R2. Okay, so this is that equation number 2, although technically I guess I called it the new equation number 2. It's this one here, the one I got after combining the original 1 and 2. And so let me use that and put current number 2 into here. So this would be E minus I3R1 over R1 plus R2 times R2. Okay, so that's that one. Equals, and let me go ahead and let's just move to the other side of the equation, the L times DI3 over I. Okay. Now, if I do a distributive property of R2 onto here, this becomes ER2. And then this becomes a minus current 3. And I've got an R1 times an R2. And each of these are divided by an R1 plus an R2. So we've got quite a bit of terms in here. And I think this would now be a good time to call something that is just a bunch of constants one symbol to make things look a little bit easier. And that's what your author is doing right here. He says call R prime the product of the two over the summation. So that right there is just what he's going to call R prime. And it might be nice to do the same thing over here, where maybe on the top we multiply by R1, but then of course to make it match, we got to do the bottom multiplied by R1. But then what we would have is we would have a group of R1 times an R2 over the summation, and so that would be an R prime. Now we would still have RE, and then it would be over an R1, if that matters. But that's a nicer looking equation, because it looks like now I can manipulate things around. I have a differential equation, and I can get my i's together on one side and my time together on the other. And so that's our standard form of solving our differential equation, get the variables on different sides. Actually, I got a little more room here, so why don't I do that? Why don't I divide both sides by ER prime over R1 minus E1R prime. because when I do that same division on this side of the equation, we're left with just the number 1. And then that way I can move my dt over to the left-hand side of the equation, and I get L over ER prime R1 minus 3R prime. In fact, maybe I should have done this earlier, but each of these have an R prime in them. And I probably should have done it back here and factor out an R prime and then left it over here. Let me do that now. So I'm going to take an R prime out of each of these and then move it to the other side. And so I'm left with, over here, an E over R1 minus I3. And I'll also take this L and put it underneath. So I've got my constants together. All right, and so now solving the mathematics here and looking back at the original circuit. Let's see, did they close or open this? What did they do? They closed it. I believe at t equal to 0, the open switch is thrown closed. All right. So at 0 time, there would be 0 current in the inductor. And then so let's integrate until time t, and we'll call it current I. All right, so this side's pretty easy. This just becomes R prime L over, or times t. And this is the one that would be a natural log. And I don't think we have to go as hard as doing a U sub if we remember that the chain rule is going to give us a -1. See, because if we did a U sub here, we would have the integral of d 1 over u, which makes then natural log of u. But the chain rule then, when you change the di to a du, would have a negative. I just like to check it and say, okay, well, let me take the derivative of this and see if I get back to here. And so if I take the derivative and pay close attention to that negative, take the derivative, I get 1 over this, so that's good. But then the chain rule of this gets a negative up in the numerator, which cancels with that. So perfect. So this does get me back. And that's why this negative, I'm going to move over here to the other side. And then write this as Ln. And so when I put in the current, it's E over R1 minus the current. And then technically minus 0 current, but when you subtract two logarithms, you can write it as a quotient. So this would be minus ln of just E over R. And then to get rid of the natural log, we will exponentiate it. We'll move this to the other side. Now we'll solve for the current finally. Move the current to the other side and move this exponential to the other side. And then finally, we get the answer. Whew. And so quite a bit of math. Like I said, it sounds real simple. And after a while, it will get real simple for you. It'll be just, look, write out the equation, solve the equation. That's how tough can that be, right? Just, hey, this is conservation of charge, this is conservation of energy. Write your system of equations and solve it. But you can see that it's got some calculus in it, and then it's got this, advanced algebra where you got natural logs and logarithms, and so there's quite a few steps. But ultimately, we did get to what they were asking, what is the current. All right. So hopefully all that was helpful. Maybe I'll finish up by saying if there's anybody still watching and wanted to do a source transformation on this, this would be a good one to do, because if you were to start with a voltage and a resistor, and then notice that resistor number 2 is not in series, but it's also not in parallel. It's neither. You kind of feel stuck and need to go back to doing Kirchhoff's laws that we talked about. And technically you are stuck, although here's what's nice about a source transformation. For those of you who know what I'm talking about, you can replace a constant voltage source with a constant current source. Where if you think about this as the electrical connector, so just kind of ignore that, this constant voltage with a resistor in series is equivalent to, and so I'll just leave the R2 and the inductor alone. Okay, so this part here can be replaced, like I said, with a constant current source. Okay, now that constant current source then would be equivalent to a current I that is equal to this constant voltage divided by resistor number 1. And I suppose that should involve some proof. I was kind of looking where that old problem, and I kind of see it there, but I'll just kind of call it for what it is and move on here. So keep in mind that this and this are equivalent. But here's what's really nice about that, is that then notice that I do have resistors now in parallel. And so now I could replace the two resistors in parallel with what they're equivalent to. Now, resistors that are in parallel, you do the reciprocal sum, which comes out to be the product of the two in the numerator and the sum of the two in the denominator. That's what in this problem your author is calling R prime. So let me just put that as R prime. And so now you begin to see a little bit of where, hey, that comes from, is you're really taking these two resistors and treating them in parallel. But how do you justify that? Well, you justify that by re-looking at the problem not as a constant voltage source, but as a constant current source. Now, I would take one more step here, and keep in mind that the constant current is E over R1. Okay, now, we solved in class a problem that had this. It had a constant voltage source, a resistor, a single resistor in series, and then an inductor. So if we do yet another source transformation, and we take this that's in parallel and go back to a constant voltage source, we would get this type of circuit, which we've already solved. So that's why I would say this one's going to be one that was just screaming at me to do a source transformation. Do a source transformation first from constant voltage to make these in parallel so I can simplify it, then go back to a constant voltage source because we've already solved it for one resistor. So I had to do something to get those two resistors to combine. So that was kind of the strategy here. So now let me do that. Let me go back to a constant voltage source with the resistor in series. And so right here, I'm kind of doing the reverse of this. I'm taking a resistor that's in parallel with a constant source and put it in series with a constant voltage. Although the thing, though, to keep in mind is that the voltage of this constant voltage source, so let me call it the new constant voltage source, would be this constant current, which is E over R1, times this parallel resistor, which is R prime. And those two aren't the same. So in other words, we don't go back to a constant voltage of what it was before. Which clearly we shouldn't. I mean, if we did, then it would have been saying, I mean, if we went back to the same voltage, it would be saying that these were equivalent of being parallel, and they're not. So there's got to be something different. It's not just that you can write these as being parallel with the same voltage. You have to write them as being in parallel with some different voltage, and that's this one. So that might be the hard part, and now that I think about it, maybe that would make this source transformation a little confusing here. But finally, I can say that I know the answer to this one because we solved it. We said that if you ever had a problem here, you would say the current is equal to the long term. And so if we had this as a V and an R, the E minus something like that, where this number out in front is the long-term current, which would be the voltage divided by the resistance. So in this case, the voltage would be ER prime over R1, that's the constant voltage source, and then divide it by that resistor that's in series, which would be in R prime. And then it would decay exponentially according to this resistance R prime and the inductor and T. And I guess the only bit of math we have to do then is to cancel those. And so we would get a current of E over R1, 1 minus E to the minus R prime over LT. So, ta-da! We got the same answer after doing a couple of source transformations. All right, well, if that was useful to anybody, great. If not, I will see you guys later. Take care.